Hello, everyone. My name is Chris Gutwald, and today Kasia Dobuchka, Laura Lancaster, and I will be talking about how to optimize formulation problems that have constraints that have been difficult to work with until Kasia and I added the new Bayesian optimization platform in JMP Pro 19, and Laura added into 19.1 a candidate set generator for linearly constrained mixture problems with the additional constraint that only K of n components are allowed to enter into the mixture. These are problems that are very common in the pharmaceutical, chemical, and consumer products industries, and we're very glad to have an easy approach to demonstrate for you today. So first off, what is Bayesian optimization? So it's a new framework and JMP platform for product and process optimization that was added to JMP Pro 19 after having been one of the most heavily requested new capabilities in the years leading up to that release. One pattern that emerged immediately was that the JMP customers that were requesting Bayesian optimization the loudest were customers that were working in product formulation of chemicals, pharmaceuticals, and consumer products. As we came to understand more about the potential of Bayesian optimization, it became clear that many of the technical problems and gotchas in working with mixture factors completely disappear, which is probably the interest was so great in those industries. Bayesian optimization, the methodology, is an optimization algorithm for maximizing a mathematical function. It has been very successful in the areas of computer simulation experiments and tuning machine learning algorithms. In the new platform, which we call BayesOpt for short, we adapted and extended the standard Bayesian optimization framework to be built right out of the JMP profiler and its desirability function-based approach to multiple response optimization. To illustrate how it works, consider the following example from the tire tread JMP sample data file where we want to find combinations of ingredients silica, silane, and sulfur to maximize the abrasion response and satisfy a specification on the ELONG response. The JMP algorithm will recommend space-filling augmentations until the model fit is satisfactory for all the responses. Once that happens, Bayesian optimization uses both the input and output values from the table, combines the model predictions from the Gaussian process models that have been fit to all the responses, as well as the prediction uncertainty from the models. Then it uses the goals for each of the responses as they've been described by the profiler's desirability functions. To identify combinations of factor settings that should be tried as the next batch of experimental runs, the promise here is that by using responses and goals to learn as we go, we hope to learn faster and to develop new products in less time and resources. At the same time, the focus on optimization via Gaussian process models means that a lot of statistical machinery like p-values, power calculations, variance inflation factors, and model effects that have to be declared in advance like interaction, curvature, and Chaffee cubic terms are all not needed or relevant in this framework. Typically, the sequence of steps flows in an order like this one with 3 distinct phases after the initial set of runs are analyzed. We begin with some starting data that may come from a space filling or custom design or possibly from a database of historical data. Then we have one or more space filling batches to fill the holes in the data until the models begin to work well enough to become useful. Then we typically have several batches that use the models to identify new factor settings to try as we seek to optimize the responses. Once the platform doesn't see much further opportunity for improvement, it starts recommending replicates of the best settings seen so far, indicating that we may be done and have possibly solved our problem. So the main reason we are here today is to learn about mixture formulation experiments. I'm going to introduce 3 levels of complexity of these designs and talk about how differences in difficulty in working on these problems with and without Bayesian optimization. The first level is simple mixture experiments where you have some factors that represent amounts of ingredients that have to sum up to some amount like 100%. These are a little tricky to design and analyze, but JMP makes it easy because you can declare factors as mixtures in the DOE setup platforms, and JMP does a lot to make handling these problems as natural as possible in a least squares based framework. The second level of complexity is multi-mixture experiments where you have 2 or more groups of ingredients that have to sum up to some fixed amount. This could happen in a recipe where you have different kinds of oils, flours, and sugars you can use as ingredients to bake a cake with. In industrial formulation, you might have groups of different alcohols, glycols, and surfactants that are candidate components to your formulation. There isn't an easy way to handle this, so you are on your own to set up the linear constraints and navigate all the model singularity problems that make the design and analysis very sensitive and error prone. There isn't an easy path to figure out how to do this, and I've run into a lot of problems going this route myself. The last and most difficult level of complexity are the cardinality constrained problems, where you have maybe say 10 alcohols and 8 glycols that are candidate components, but for practical reasons, you need to have no more than 3 alcohols and 2 glycols because otherwise the supply chain and production process will be too complicated. This is a universal problem that probably comes up all the time. I don't know of any easy way to design and analyze this situation in JMP 18 without tremendous difficulty. I want to point out that the cardinality constraint can happen in single mixture and multi-mixture situations, and it could even be applied more generally to any set of continuous factors. Most of the problems designing and analyzing complicated mixture experiments using classical methods stem from the fact that least squares models are based on a design matrix that must not have any linear dependencies amongst the columns. And mixture problems always have at least one or more linear dependencies amongst the factors. This is manageable with simple mixtures, harder with multi-mixtures, and extremely difficult, if not impossible, to deal with cardinality constraints. Gaussian process models are distance-based rather than design matrix-based, which makes all of these problems basically disappear. Fortunately, Laura's new JSL function in JMP Pro 19.1 and the Bayesian optimization platform that Kasia and I developed have made the impossible possible, and hopefully what was impossible in the past will be made easy in future releases. Now I'm going to hand it over to Kasia, who's going to show how easy simple mixture problems are with Bayesian optimization.
Okay, so let's take a look at a relatively simple mixture problem and how you can approach it in JMP Pro. We want to produce a lipid nanoparticle, which has a potency and molecule size we want to optimize. We have 4 types of lipids to combine: PEG or PE glylated, a helper lipid, a structural lipid, and an ionizable lipid. We have limits on how much of each ingredient we want to use, and we have 2 types of ionizable lipids we're considering. Finally, we mix them using a variable flow rate and NP ratio, which are continuous factors, and we get our lipid nanoparticle. So let's discuss the 2 ways we can set up our data table. The easiest way is through the custom DOB platform. We just enter all our responses and how we want to optimize them, and then enter our factors. You just denote the mixture variables accordingly and enter the proportions we want to limit them to. We can use this to generate a starting data set in an appropriately formatted data table. Alternatively, we can set these properties up manually through column properties. If you already have some starting data, this may be preferable for you. We can open the column properties for our mixture factors and assign them the mixture design role. And then we can go to the mixture property and fill in the proportion limits manually. For the non-mixture factors, we just fill in the possible levels in the case of categoricals, or the ranges in the case of continuous factors. Finally, for the responses, we fill in the response limits properties with our goals. So for the potency, we want to maximize past at least 98 units, and for particle size, we want to maximize past 50 units. Regardless of how we set up our starting data, we can now launch the Bayesian optimization platform, which we call BayesOpt for short. We fill in our X's and Y's, and optionally, we can specify how many points we want to recommend at one time. Let's say for our process, we have a machine that can run 3 different samples at a time, so we'd like to choose 3 new points to sample next. We hit OK and get to the platform. The next samples have been automatically chosen from a large, automatically generated candidate set. In the case of data with constraints, we leverage the built-in prediction profiler's data generation method. You can see, if you look closer, that the mixture requirements are indeed being respected. The 4 mixture ingredients do indeed sum to 1, and each component is kept within the desired limits. If we're happy with the generated points, we can hit Make Table and be done with our platform in 1 click. Going back to our data table, we have our new points added to our table, ready to be sent to the lab for sampling. Notice that the platform has created these 2 new columns. The iteration column records which batch each row belongs to, with batch 0 representing the starting data. And the reason added column automatically records why each point has been selected. So once our responses have been collected for our new points, we're ready to launch BayesOpt again. To do so, we can use the startup script that was saved by the platform. Running it launches the platform and automatically remembers which X's and Y's you were using and other relevant settings like the batch size we requested. Having run the script, we're taken straight to the new batch recommended by the platform for our next iteration. We can then hit Make Table to export, and from there, we can just repeat the process until we're satisfied. So jumping ahead several batches, we see that the 6th batch we've generated includes a replicate of the best point so far. That indicates that the platform is fairly confident we can't improve much farther. Just a sanity check, we can collect responses for that last batch and launch the platform one more time. Since the platform wants to continue replicating, that indicates that we're quite confident in our optimum. But this was a fairly simple mixture problem. Laura is going to help us tackle more complicated constraints next.
So Kasia just demonstrated how easy it is to use the Bayesian optimization platform for a simple mixture experiment. I want to talk about the more complex formulation problems that Chris introduced earlier. He talked about multi-mixture experiments that contain more than one mixture, have a mixture of mixtures. He also talked about cardinality-constrained mixture experiments. Those are experiments that have restrictions on the number of components allowed to be non-zero in at least one group. He noted that both of these types of complex mixture experiments were very, very difficult or even impossible to design and analyze with the classical methods before JMP Pro 19. So now I want to talk about the tools in JMP Pro 19 that make these complex formulation problems very, very easy. So the first tool is, of course, the Bayesian optimization platform. The first way it helps us is by using Gaussian process models, which sidestep the singularity issues present when using classical models. The second way it helps is by allowing the user to supply a candidate set during the optimization iteration. If we can supply a feasible candidate set that obeys all the mixture and cardinality constraints, then we can quickly find a feasible optimal solution. So now the question is, well, how do we get a feasible candidate set when we have complex mixture and cardinality constraints? Well, there's actually a new JSL function in JMP for generating feasible candidate sets. This function generates random samples that are subject to linear constraints, variable bound constraints, and cardinality constraints on groups. Once we have a feasible candidate set, we can supply it to the Bayesian optimization platform for use in each optimization iteration. Additionally, you could also potentially use these candidate sets to create your own initial design. And note that with the Bayesian optimization platform, you can use initial starting designs that are actually quite small, but still quickly lead to an optimal solution. So this new JSL function is called random linearly constrained uniform, and it actually expands and replaces the old polytope uniform random function that has been in JMP all the way since JMP 8. And note that using the old name will still work as it did before if you have scripts in place already. This new function will actually be available very soon in JMP 19.1. But before we talk about the new features of this JSL function, let's talk about the behavior of the function up until JMP 19.1. So this JSL function, formerly known as polytope uniform random, uses Robert L. Smith's hit and run sampler algorithm to generate a sequence of points in a linearly constrained and bounded region. This algorithm has the nice property that the random sequence asymptotically approaches a uniform distribution over the constrained region. The algorithm is shown in the slide above, but the basic idea is that once we find a feasible point inside of the constrained region, we take steps of random length in random directions that stay within the constraints. It's actually easiest to understand with a visual demo, so let's look at one now. Now suppose that this is our constrained region in which we want to generate random points. The first thing that we do is find an initial feasible point. We find the initial feasible point using phase 1 of a linear programming algorithm. This initial point is actually on an extreme point of the constrained region, but we need to get inside the interior. So now we generate a random feasible direction from this point. Then we find a random feasible point along this direction. Once we do that, we have our starting point that is inside the interior of the constrained region, and we have our first point. From our first random point inside the interior, we start generating random directions and finding feasible points along the random directions. We generate a random direction and find a feasible point along that direction. This gives us our second random point. From the second random point, we generate another random direction. Then we find a feasible point along this direction. Now we have our third random point. From the third point, we generate another random direction, find another feasible random point along that direction, and so on until we have the desired number of random points. So here's a picture of 30 random points inside the constrained region. Now let's talk about the expanded functionality of the random linearly constrained uniform function that is new in JMP 19.1. It will be able to handle the cardinality constraints in addition to the linear and bound constraints that the function could previously handle. This is a general flow diagram of how the function algorithm works. So let's just walk through it very quickly. The first thing you want to do is to initialize your problem and the constraints and set up the number of points that you want to generate. Then you're going to randomly select a number and group components to be included in the formulation according to your cardinality constraints. Then you want to lock the group components that you didn't select at 0. Then you're going to set all the constraints to the hit and run sampler to generate a random point with respect to your linear constraints, your bounds, and your locked variables. Once you get your point, you ask yourself, do we have enough points? If we do, then we stop. If we don't, then we're going to reset all the variables that we locked to 0 and start over, keep going until we get the desired number of points. Let's look at a simple example to see how this function works. So the image on this slide shows a formulation problem for finding an optimal 500 milliliter smoothie. We want to find the optimal mixture of fruit, yogurt, and ice needed to create a smoothie that tastes great and is nutritious. All of the ingredients must sum up to 100%, but additionally, we can only choose between 2 to 4 of the 6 types of fruit because of cost and production constraints. This is a list of the constraints for our smoothie. We have the bound constraint, the mixture sum constraint, and the cardinality constraint where we can only choose between 2 and 4 fruits. And I have checked which of the components are subject to the cardinality constraint. So now let's look at how the algorithm would work. First iteration, first thing we would do is randomly select the number of fruits that we're going to include, and we chose 4. So we need to choose which 4 fruits are we going to choose. We choose peach, blueberry, strawberry, and banana, and that means we are going to lock cherry and pineapple at 0. We send this to the hit and run sampler to generate a random feasible point, and we get a point out that satisfies those constraints. We have 1 point. Then in the second iteration, this time we randomly select to choose 2 fruits. So then we randomly select the fruits we want to choose, the 2 fruits, strawberry and pineapple. We lock all the other fruits at 0. Send this to the hit and run sampler to generate a feasible point according to these constraints, and we get a point. And so on until we get to 1,000 points. So now that we have an idea of how the new JSL function works with a simple example, let's look at a real-world complex formulation problem for a polymer. Here we have a small example where we want to find an optimal formulation for a polyester. We've identified the 4 polyester properties on this slide as the critical qualities that we want to optimize in our formulation. Our goals are to have an inherent viscosity of 4 deciliters per gram, so that's our target, and then we want to maximize the other 3 qualities. This slide shows the materials that we are considering for making our polyester. They are divided into 3 groups. The first group on the left shows the acids that can go into the acid mixture for this polyester. We can only have 1 or 2 acids in the formulation. The second group are the glycols that can go into the glycol mixture for the polyester. We can only have between 1 to 3 glycols in the formulation. The third group shows the other materials that go into the formulation that are not part of a mixture. Acid number and hydroxyl number are continuous factors, but reactor is actually a categorical factor that is either A or B. Because we have two separate mixtures and cardinality constraints on each mixture, this is a formulation problem that would have been very, very difficult to design, model, and optimize before JMP 19. But I will show you how we are going to generate a candidate set for this problem, and then Kasia is going to show you how we use the Bayesian optimization platform to find the optimal polyester formulation. So this is a list of all the mixture sum constraints, the bound constraints, and the cardinality constraints for our problem. And our JSL function for generating the candidate sets does not yet handle categorical variables, but there's a trick we can use. I'm just going to use a continuous factor and set it between 0 and 1, and then I will show you how we can convert that to a categorical factor later. I don't have time to go into the details of how to use the JSL function, but this is, but there is a description and some examples in the JMP object scripting index under the help menu. And here is an image of that explanation and description. So now let's go to JMP 19.1 to see how this function works. Okay, so I'm going to open up the script that I created, and here it is. I don't have time to go through it in detail, but this script is saved to the community, so you can look at it, and it's got lots of comments that you can read through to understand it. But in a nutshell, I have set it up to generate 150 points. I set up the linear constraints, so these are the two mixture constraints. I've set up the bound constraints, and this is the cardinality constraints, and then this is the code to call the random linearly constrained uniform. So it's going to generate 150 points and then send them to this variable, which is a matrix called SimPoints. Then I'm going to turn that variable into a data table. So I'm going to go ahead and run this script. It doesn't take very long. It generates the random points and creates a data table. Because it's just creating a data table from a matrix, the columns don't have very interesting names, so you probably want to rename them. But I did want to point out how I'm going to change this first column to my categorical variable. Remember, I set this up to be between 0 and 1. So what I'm going to do is I'm just going to change anything that's less than 0.5 to A and anything that's greater than 0.5 to B. And I have a script right here to do that very quickly. You can also just use a formula if you'd rather. And I can quickly convert it to a categorical variable. Now, really want my table to have more interesting names and to be cleaned up a little bit. But this is an example of the cleaned up data with new names. And this is actually a set I generated with 15,000 runs. And this is what Kasia is going to use to run the Bayesian optimization platform. So I'll hand it over to her.
So let's take a look at one of these more complex examples. Like Laura explained, this polymer formulation problem has several constraints, including multiple mixtures with cardinality constraints. To summarize the problem, we're creating a polymer which has 4 response metrics we wish to improve simultaneously. We have 3 metrics we want to maximize past certain thresholds, and we have 1 metric we want to match a specific value as close as possible. In this example, we have 45 observations to start with. We have 1 categorical process factor and 2 continuous non-mixture components. And finally, we have a mixture that must use 1 to 2 of 6 available acids and a mixture of 1 to 3 of 6 glycols. The big challenge here is the 2 mixture components, each with a cardinality constraint. Because of that, we can't just use the profiler to generate a candidate set for us because the constraints are too complicated. Instead, we have used Laura's JSL function to create a candidate set of 15,000 possible sample points. Each time we are picking new points, it will be from this menu. So launching BayesOpt, we fill in our factors and responses and optionally set our batch size to 2. Let's say in this example, we have 2 available mixers, so we can run 2 at the same time. Once the platform is open, we go to the red triangle drop-down menu in the Batch Selection tab and click Load Candidate Set. Using the pop-up, we select the candidate set we made previously. Once the candidate set is loaded in, the platform automatically selects a batch of our desired size. If we're happy with the automatically selected points, we can hit Make Table and move on. Before we do, we can open this drop-down menu of export options. In this case, let's enable including the original candidate set row indices so we can keep track of which rows in the candidate set correspond to our selected batch points. Like before, we can see both the new batch points and the documentation columns added to the table. In addition to the default iteration and reason added columns that we've seen before, we see a third column has been added. Those numbers correspond to rows in the candidate set. So in our case, we had 15,000 available points, and we chose to use the 2,867th and 5,317th points out of those. Once we collect our responses, we can launch the platform. To tease a feature coming up in version 20, our automatic scripts will be able to load your candidate set in automatically on launch. However, for the time being, we will have to load in our candidate set every time we launch the platform. Regardless, we open the platform, load our candidate set, and automatically get 2 new suggested points. And from here, we can repeat the process. Looking ahead to batch 13, the platform has chosen to replicate the best run so far, indicating we may be done optimizing. But what if, after replicating the sample point, we see a much worse response than the first time around? Investigating the desirability run chart closer, we noticed the desirability became far worse, despite having the same factor settings. It's possible that this set of factor settings simply has a lot of noise. Alternatively, we can investigate the model summaries, where we see 2 of our response models have very large error. And this is reflected in our observed responses. Despite the same factor settings, run 68 scored 85,000 in one response, and run 70 scored only 66,000 in the same response, which likely contributed to the steep drop in desirability. So either way, these results tell us we might want to investigate further. Looking ahead a few more iterations, we see that BayesOpt automatically recognized the replicate was significantly worse than the original and knows to continue searching. We see the platform has chosen different runs as potential optimums to validate, while the other points are used to explore further and try to improve our prediction accuracy. Looking at the updated run chart, we see the last point to be replicated has had high desirability both times it's been sampled, and this tells us we may be right to have reevaluated. If we continue sampling even further, we see BayesOpt is now more confident in the optimum it has found, since it is continuing to suggest replicating it. Looking at the desirability run chart in platform, we notice that these points aren't actually the best we've seen. However, we see it consistently performing well, indicating that it's a more consistent optimum than the other peaks we have tried replicating. So just to review, BayesOpt makes most mixture experiments easy to design and analyze, and makes complex constraints much easier to work with. Through the candidate set loading feature, if you can build a candidate set of points that satisfy your constraints, then BayesOpt can help optimize your problem. With convenience features like script generation and automatic documentation, the entire process of sequential experimentation is intuitive and easier to manage. And that is all from us. Thank you so much for attending and watching.